Hello everyone. So we already have covered different concepts related to semiconductor physics and semiconductor devices, and recently in previous few lectures we have seen what are the different considerations associated with MOS capacitor. MOS meaning metal oxide semiconductor capacitor, and prior to that we also have discussed concepts related to PN junction, BGT, so on and so forth. In each of these topics, we also have discussed numerical problems, how to solve numerical problems, or how to solve, say, a question when you get, and what should be the approach. So, today also we will have a numerical session on MOS capacitor primarily, and then we will see what are the different types of questions that you can expect from MOS capacitor. We also have discussed different problems related to basic semiconductor physics, and when we solve problems related to devices, we may need those concepts and those equations. So, we will directly use the equations in these problems. However, we already have discussed those equations sometimes briefly and sometimes in details. For example, the major equations we already have discussed in theoretical discussions in previous lectures. So, let us start this lecture and see what are the different problems that we may get in MOS capacitor. So, we will just show you a couple of problems related to MOS capacitor, but you can expect similar type of problems in different examination. Every time I say when I discuss the numerical problems that it's not only solving different questions for different examination, it is also to understand that how these problems can be applied in real life scenario, or how real life scenario problems actually can be solved using different numerical equations or techniques that we have studied. So, this is the basic purpose of showing all these numerical problems. At the same time, I would also say that if you apply your mind beyond the question idea, you can also find noble ideas to convert these devices into a sensor. And one more thing that I request in almost all the numerical problem solving sessions is to go through the question very seriously, and to the extent you can understand each and every word of that particular problem, because each and every word of this question will carry certain sort of information, which at times you may feel that this particular line is not important or this particular word is not important, it is just given for the sake of completion of this question. But if you read that particular phrase, or if you read the entire question, and if you can think of different other phrases or questions in that, or parameters in that particular place, you will see the entire problem will change. So, this part is also very important. So, let us see the first question that we have. So, the first question is calculate the capacitance Cox and Fermi potential phi Fp for a MOS capacitor. Consider a p-type silicon. Consider a p-type silicon substrate at T equal to 300 Kelvin doped to Na is equal to 10 to the power 16 per centimeter cube. The oxide is silicon dioxide with a thickness of Tox 18 nanometer, which is 180 angstrom, and the gate is aluminum. Now, in this particular question, as I have said, if you go through the entire question and consider each and every word, for example, it is written calculate the capacitance Cox. So, it is quite evident that when it is written as capacitance and given Cox, so it is oxide capacitance. You have MOS capacitor, you have metal, oxide and semiconductor. So, this is what it means. And Fermi potential phi Fp for a MOS capacitor, right. Now, it is mentioned that it is a MOS capacitor. So, just to give you an idea, for example, if it is not written that for a MOS capacitor, then Cox could be in different other context also. Cox could be different things. Now, in this particular session, if I do not write MOS capacitor, it is well understood because we are discussing MOS capacitor. So, if I mention Cox, it is definitely Cox of MOS capacitor. But when it comes to a general context of semiconductor physics, and if it is only said calculate the capacitance Cox, it may become confusing. Cox of which configuration? Even the term Cox is valid for MOSFET, that we will see, because in MOSFET also you have a MOS, and maybe in other context also the term Cox can be valid. So, that is why it is very important that this particular terminology or this particular thing is explicitly mentioned that it is an MOS capacitor. Consider a p-type silicon. So, it is also written that consider a p-type silicon. Now, when I solve the problem or when the problem solution is complete, when the solution is complete, you can think that what if it is an n-type silicon? It is written a p-type silicon substrate. This could be an n-type silicon substrate as well. Whether there will be a change if there is an n-type silicon substrate, or the problem or the solution remains the same. That is, these are some considerations that you can think after the solution is complete, just to enhance your idea, just to enhance your understanding at T equal to 300 Kelvin. So, it is also written temperature is 300 Kelvin. Now, when T equal to 300 Kelvin, we often ignore that part because all the equations, all the calculations that we do in semiconductor physics, as of now what we have seen different values, they are usually in 300 Kelvin. But what if it is 400 Kelvin? Probably the problem will become little more complex because you need to then calculate everything for 300 Kelvin. Then it is doped with Na 10 to the power 16 per centimeter cube. Now, see, because it is already written p-type, so definitely this should be Na. Now, in some questions, you may find that this Na term is not written. They are only, probably they will only mention, consider a p-type silicon substrate at T equal to 300 Kelvin doped to 10 to the power 16 per centimeter cube. So, it is quite obvious if it is in p-type silicon, this should be Na, that is acceptor ion concentration or acceptor atom concentration, right. The oxide is silicon dioxide. So, this also is mentioned with a thickness of Tox equal to 18 nanometer, and the gate is aluminum. Now, in this thing, one more information is the oxide is silicon dioxide, and we know if we are going to calculate the capacitance, we need the value of epsilon. Now, what is the value of epsilon here? It is not given, but they have mentioned it is silicon dioxide. Now, for silicon dioxide, the epsilon value is 3.9. This is something that we know. That is why they mentioned the name of the material, but not the value exactly. So, these are some considerations that you always have to keep in your mind. Now, what if the oxide is not silicon dioxide, say it is hafnium oxide or some other material, aluminum oxide or some other oxide or some other material, other dielectric, then this value will change, and it's not possible to remember all these epsilon values for each and every material, but for very well known materials, it's better that you remember some of the values. And then it is written the gate is aluminum. Now, whether this information has something to do with this question or not, that we need to also think. What if the gate is not aluminum? What if the gate is polysilicon? What if the gate is say gold? Will anything change? So, these are something that you can consider after the problem after this solution process, when we solve the problem, you can think at your home. Now, as far as the question is concerned, it is not very complex because we already know the equation of Cox, which is epsilon ox by T ox, that we already have seen. Now, the value of epsilon ox 3.9 into, we know the value of epsilon 0. So, this is epsilon ox means epsilon r into epsilon 0. So, it is 8.85 into 10 to the power minus 14. So, this is what the value is, and then you have the T ox value also given, which is 18 nanometer. So, 18 into, or you can write 180 into 10 to the power minus 8. Now, this value will give you some equation, a unit, not equation. This value will give you an unit which is farad per centimeter square, because this is written in terms of centimeter, right? 18 nanometer is 18 or 180 angstrom is 180 into 10 to the power minus 8 centimeter. And then if you do the calculation, you will get the value which is 1.9175 into 10 to the power minus 7 farad per centimeter square. So, this is what the value of Cox, and this is very important that we always keep an eye on each of these parameters that are given, right. Now, when we are calculating this Cox, you can see that only two parameters that are given in the question are being used, but there are many other things also, many other things, meaning at least I can see the value of Na that is given. Now, at least for this calculation, for the calculation of Cox, we did not use the value of Na, but now we have to also calculate the value of phi Fp, which is Fermi potential, or you can call it as bulk Fermi potential, which is Vt ln Na divided by Ni, and the value of Vt is 0.0259, that we already know, that we already have calculated before. So, I am just using it right now. You probably have seen in previous problem solving sessions, and then you have ln, the value of Na is given. So, the value of Na is given for calculating this phi Fp, which is Fermi potential, and then we have the value of Ni, which is 1.5 into 10 to the power 10. So, when it is written as silicon, so the value of Ni at T equal to 300 Kelvin is also sort of known. So, this value also you can keep in your mind, and finally, when you do the calculation, you will get the value is 0.3473 volt. To do this calculation, you will get this value. So, this is what the Fermi potential. Now, you can now see that the parameters that are given here, almost everything is used. So, T equal to 300 Kelvin is important, because if this is not given, then you do not know what is the value of Ni. Value of Ni will change based on the temperature. Then we also have used Na, because in order to calculate the Fermi potential, we need the value of Na. And then again, T equal to 300 Kelvin is important, because we need the value of Vt. So, at different T value, that is different temperature, the value of Vt also will change. So, this is a simple problem, but you always need to understand the question, and you also need to understand that each and everything given in the question is important. Now, in this case, you can see that this information that the gate is aluminum is actually not that important as of now. It could be polysilicon also, probably for that also this calculations would be same, but in some cases you may find that This information is also important. At least we know now what is the metal used in this particular device, right. So, let us now go to the next problem. So, in the next problem again we need to calculate the flat band voltage for a MOS capacitor with a p-type semiconductor substrate. So, this time it is written p-type semiconductor substrate, it is not given that it is silicon as of now. Consider the MOS capacitor with a p-type silicon substrate. So, now it is mentioned. So, the semiconductor material here is silicon. Dope to Na is equal to 10 to the power 16 per centimeter cube. A silicon dioxide insulator with a thickness of 20 nanometer, TOX equal to 20 nanometer or 200 angstrom, and an N plus polysilicon gate. So, this time the gate is polysilicon. Assume that QSS dash is equal to 5 into 10 to the power 10 electronic charges per centimeter square. So, electronic charges meaning it is 1.69 into 10 to the power minus 19 coulomb. So, we need to multiply this with this value, right. Then only we will get the value of QSS dash. So, this is 1.69 in 1.6, you can consider 1.6 into 10 to the power minus 19, right. Now, again another information is given is the work function difference here is QMS is equal to minus 1.1 volt. So, this information is important because this is metal to semiconductor work function difference and this is given here. Many cases probably they will provide you some energy band diagram where this value is indicated, whether it is 1.1 volt or whatever it is. But in this case there is no such band diagram is given. So, the value is already given that the work function difference here is minus 1.1 volt. Now, we need to calculate first. So, we need to calculate the flat band voltage. Now, the equation for the flat band voltage is VFB is equal to the work function that we have minus QSS dash divided by COX into this is what the value is, right. This is what the equation is. Now, we have almost all the values present. For example, this value is there, this value is there, but we need to calculate COX. COX is nothing but epsilon aux divided by TOX. Epsilon aux in this case is 3.9 into 3.9 because it is a silicon dioxide insulator. So, we can consider this as 3.9, 8.85 into 10 to the power minus 14 divided by TOX is 200 into 10 to the power minus 8, this is centimeter. So, ultimately the value we will get is farad per centimeter square. So, the value if you do the calculation would be 1.726 into 10 to the power minus 7 farad per centimeter square. So, this is what the value of COX is. Now, you can also calculate the value of QSS dash, which is 5 into 10 to the power 10, that is written over here, and then into 1.6 into 10 to the power minus 19, which will give you a value of 8 into 10 to the power minus 9 coulomb per meter square. Now, this QSS dash is basically equivalent oxide charge density. So, this is nothing but equivalent oxide charge density. We also have discussed this in the theory. Maybe the notation that we are using here is different from what we have used in the lecture, but the equation is similar. So, in this case phi ms is minus 1.1 volt minus your QSS dash, which is equivalent oxide capacitance, equivalent oxide charge density is 8 into 10 to the power minus 9, and then Cox is 1.726 into 10 to the power minus 7. Now, if you do this calculation, you will get that the value is minus 1.15 volt. So, this is what your flat band potential is in this case. So, again the solution to this problem is not very complex, but we need to read the question very carefully, and we need to understand why these parameters are given. Sometimes some parameters are additional, some informations are additional in the question that are actually not required, but these information may sometimes become misleading. So, a simple question may become a trick question just in case a few more additional parameters or additional information is given in the question. So, one has to be very careful, and one has to be very kind of mindful when they read the questions, and always note down the parameters that are given, because that will help you to simplify the entire situation given in the question. So, this is how one can approach to different problems related to MOS capacitor. There are many other problems related to MOS capacitor. I would recommend all of you to also solve other problems from other sources and practice it, because practice is very important. Again, before I conclude this lecture, I would say that always be mindful about the units that are given, what unit you are using. For example, here I have used the unit centimeter. In case of the TOX, we could use meter also, but it depends what are the other units present in the question, meaning units of other parameters. So, if most of the parameters are in centimeter, then if you do it in centimeter, it is much easier. Otherwise, you have to convert everything into meter, and that is an additional work. So, you have to be little smart also in this case, but nevertheless, I would recommend that you go through the physics, you go through the equations, keep some of the values in your mind. For example, here we have used the epsilon value of silicon dioxide as 3.9, because we know that is why, and it is also not given over here. And I mentioned before, some of the parameters may not be available in the question. So, you can't write that information is insufficient, because information is given, it is in silicon dioxide insulator. So, some expectation will be there from the whomsoever is asking the question, that at least this much you know, the value of epsilon in for silicon dioxide is known to you. So, these are some of the expectation from the question maker that you should know. So, you can't just write that this information is missing in these cases. So, you can also go through dielectric constant of some other known parameters also, there is no harm in it, but the basic thing should be known. So, let us conclude this particular lecture, and always keep an eye on different parameters. If you change something very minutely, or if you change something, some information to some other information. For example, what if it is an N-type semiconductor substrate? Why only P-type semiconductor substrate related problem is given? What will happen if say this gate material is not N plus polysilicon but something else? For example, in the last question it was aluminum. So, these are some critical thinking that you can always think and keep it as an homework, that okay, if you sit with the problem for half an hour, you can actually make 50 new problems from the same problem only. Just by changing some information here and there, it becomes a different problem, right? And at the same time, also think how these information can be used to design a novel device, a novel sensor. just by changing some parameters. So, you are getting a flat band potential of this much, the oxide capacitance is this much. For example, what if I change the dielectric, that is silicon dioxide, with a material that say absorb gas, and the dielectric constant changes based on the gas absorption. So, this probably would be a sensor which can detect gas, because more the concentration, more will be the absorption, more will be the change in MOS capacitance, this Cox value. And if you can actually get this value out as an electronic output, then you can calculate the concentration of the gas in that particular environment, something like that. So, these are some critical thinking that can convert a conventional device to a electronic sensor. So, let us conclude this lecture today. We will meet again in the next week with more concepts and more information associated with semiconductor devices and semiconductor physics. Thank you very much. See you again.